Having studied the regression problem, let us investigate into the case where we can have different regression functions that depend on the data sets, and what if we can comment on the bias and variance evaluated over these data sets over different data points, right. So, let me set up this problem slightly carefully. Consider the functional approximation problem. We have a data set D and an associated mapping f from x to y. What this typically means is f of x y equals f of x, I say y equals f of x. So, note that x can be a vector and y could also be a vector, but in a multi-class problem y can be the label and it can be a scalar and x can be a vector, or it can be the case when x and y both are scalars, right. So, typically in most classification problems this capital Y can be a small y which is a scalar and x can be a vector. So, this is just a note for your consideration. I will just mark it here, it can be a scalar in label associations and x can be a feature vector. We need to get a good estimate of f from the data set, and typically f is unknown. We are having a system, it spits out values of y and we do not know the explicit form of this unknown function. Now, how do we approach this problem? Now, given a data set D, I want to get a function g that depends on the data set D, which is as close to the unknown function in some sense. This is very important. What sense? We have to define a performance metric like we have done earlier. It can be the mean square error, it can be the likelihood function, it can be variety of functions that we are interested in, right. So, this is a small detail. Now, you may question at this stage, do I have only one data set? Typically not, because if I am sampling I can formulate different data sets, I can form different data sets, and depending on the data sets I have this association between x and y, okay. So, therefore, this function g depends on the data set. Now, we have different data sets d suffix I going say from 1 to n, and I will sort of mention this here, I equals 1 to n, and given these data sets we can arrive at various estimates of the unknown function, okay. I think this setup should be sort of clear, because we cannot sample the function completely, because we can have infinite values and typically we do not have space to store all the infinite values, we have just finite records. So, we sample at certain points under certain conditions and we record these data sets, okay. Now, let us see this example slightly more carefully, but before then I would like to sort of give you a picture about this sampling. Imagine that there is an association of feature vectors to possibly an animal, like let us say a cat. We have varieties of cats and associated with all these cats there are feature vectors, right. You sample certain data sets and you label them, these are the cats, and these are not exhaustive. I can have varieties of feature vectors which in some sense are associated with the family of cats, right. And this is the subtle detail when we talk about sampling the function and forming these data sets and associating a label to these points. Okay. This picture becomes very clear when we delve into the visualization. So, let us consider the parabola here. This is the blue curve, it is a parabola. Let us say I am given just 2 points from this curve, just 2 points from this curve. What 2 points do I have? For example, I can have a data set D1 comprising of these 2 points on the left side. I can have data set D2 that have these 2 points on the right side of this blue curve. I can have a data set D3 that has these points towards the bottom of the curve. Suppose I ask this question that I need to fit a line of the form y equals mx plus c to these data sets. What is the line that I can fit, right. So, given data set D1, I just connect these 2 points through a line. It is straightforward, I can get an estimate of m and c from straightforward coordinate geometry. So, I get line L1 passing through these points. Similarly, I get line L2 passing over the points in the data set D2, line L3 going through the points in the data set D3, and so on. Now, one may ask this question, if I want to fit this the points with just a scalar, that is I just have one variable which is just a scalar. Now, I have 2 variable, I have 2 parameters, the slope and the intercept, and I fit a line, right. But instead of fitting a line, I just want a point which is a best representative of this blue curve, which is this parabola. Then what do I do with this, right, and what can I comment about the goodness of my fit, so on and so forth. These are sort of general questions, and in general, if we were to extend this, suppose I increase the model complexity, right, from a single scalar to a line to possibly a function which is having a power of x which is x square, or a cubic function or a quartic function, blah blah blah, so on, to an nth order polynomial. I can think of various forms of complexity in terms of the model itself. Is there a trade off that exists with the model complexity that can approximate this function, right. These questions naturally arise to us when we discuss with the regression problem. Okay, let us go slightly deeper into this problem, trying to get a sense of intuition to what we are trying to build towards our analysis. Now, imagine I have a space of functions, and in this space of functions I have just one function which is g, right, which is acting on this data set, right. So, I have only one function acting on this data, and then I have this true function which is unknown. If I were to compute the deviation of g of x minus f of x, because I do not know f, I come up with an approximation to f which is g, which is a function of x, that is the data points. Clearly there is a bias, and this bias is given by this quantity, this deviation, right. This is the bias that I can have. But is there a variance here? There is no variance because we just have just one function which is acting on this data. Let us extend this carefully to the situation where we have a pool of functions gi. Okay, as usual you can imagine that I goes from 1 to n, capital N, and these gi's agree with f on the training data sets d suffix I. Again I going from 1 to n. I do not have space here, but it follows straightforwardly. Now you have a data set d suffix I, and associated with this training data set d suffix I have a function g suffix I that agrees with the true unknown function. Now we can have a subset in this space. So now this is a pool of functions, right. This is what I write here is basically pool of functions, this outer circle, right. There could be a subset of functions within this pool of functions, I call the subset S, that are quite close to the actual function f. You have to be slightly careful in your understanding here, because g suffix I depends on d suffix I, like the example that we considered in the parabola. Depending upon where I am sampling, I get a different line. So here I can have a different function g suffix I that depends upon the data set d suffix I. So here, since all of them are in this vicinity close to f, the bias could be much small, but the variance could be high because we have more than one function, right. Here we just had one function, therefore there was no variance, and here we have more than one function, so we are bound to have a variance, right, that depends on x. Now having seen that there is bias and variance in the error averaged over the data sets, because you have an error, right, you have a deviation from the estimate of this function that you have evaluated over the data set to the true unknown function. So there is an error, and now you can compute the statistics, you can compute the bias, you can compute the variance of this. So therefore you can do these computations, you can compute the statistics. From this you can arrive at some intuition, what we started off with earlier, that there is a trade off between bias and variance. So if I had a single function, right, I have some bias, no variance, but if I have a pool of functions, my bias is less because I am close to the true function in terms of deviation averaged, and I have variance which is not 0 because I have many functions there. So there exists a trade off between bias and variance, and this is the bias variance dilemma that we need to tackle in regression problems. Question is, can we analyze this further? What is this trade off and how can we go about with the analysis? Okay. Now with that in mind, let us delve a little deeper into our understanding of the role of bias and variance. I told you earlier that when we were looking at sampling the parabola with just 2 points and trying to fit lines, right. I can have different lines that depend upon the data sets that I have or the data points that I have sampled. Suppose I increase the model complexity, right. If it was noiseless, a second order curve would be a good fit to the set of points. I can fit a parabola ax square plus bx plus c, I can fit ABC given the points exactly. In practice it may not be so, because our measurements invariably have noise associated. This is very important and noise is fundamental. Now given noisy samples, if we increase the model order, we can accommodate noise, we can let the curve pass through these noisy points, because we are approximating, we are going from second degree, third degree, fourth degree polynomial. So if I want a 4th degree polynomial that I want to fit with noisy samples, I can have a curve which is a quartic function, which is a 4th degree polynomial that can fit these points, and it fits noise as well, but it is an overfit for the model, because the true function is a quadratic function, but we are fitting a 4th degree polynomial for this. Let us try to visualize this through this figure here. We start with this parabola, which is our true unknown function, which is f of x, right. Now these red circles that I have are the sample points, and they could be potentially noisy, they can be away from this curve, right. For example, here at this point this is away from this curve, you can see this away from the curve, away from f of x, but this is my data set. So I sample some points that are noisy, I get a curve g1x that I can interpolate these points depending upon the model complexity that I have. Bear in mind that I am also fitting noise through this curve. Similarly, I can choose another set of sample data points, let me call that as D2, and I can fit a curve G2 that can go through these points, right, so on and so forth. But I can also have an average curve which is computed from all of G1, G2, G3 so on till G suffix capital N. So therefore I can have a sample mean curve, which is this G bar of x, which is the mean of all these curves G I of x, okay. So therefore with different data sets I can fit different curves, and there is a mean curve associated, which is this G bar. So at this point you may wonder, would I have to do the sample mean or I do this statistical average over a distribution of these curves. So we will talk about this expectation towards the later part of this lecture, but assume at the moment G bar is computed using the sample mean, but there is no hard and fast rule. You could do the expectation over all the data sets and you can compute the average that way. We can define two quantities, which is a bias of x, which is given by this average curve G bar of x minus f of x. This is the deviation from the average fit that I have over these data points with respect to the true function f of x, which is unknown. And I can also define the variance of x to be this quantity g suffix d of x minus g bar of x. So g suffix d of x indicates that it is a curve with respect to this data set D, g bar is this average curve, and I take the square of this deviation and I average it over all the data sets D conditioned to x, right. So, this depends upon the points x, right. Now, within this context we want to study this issue of bias variance dilemma, right, bias being less and variance being more, etc., right. And you, if you are savvy, you can think about the case where it is noisy, where the case is noiseless, and if it is noisy the variance gets additive because of the noise, right, which is a squared positive quantity. So, you can expect that this squared error would be more and averaged over the data sets and the set of points. Now, let us work out an analysis of this regression problem. So, y equals f of x plus epsilon, f is an unknown function. In the very beginning of this lecture I told that x and y could be vectors, but I will assume here that x is a vector possibly and f of x is a scalar valued function which is giving me y, right. And typically for these labeling problems, if you think about class labeling problems, this function could be just a label and probably it is more intuitive to have y to be a scalar, but you do not have to be restricted towards that. Epsilon is the regression noise which is a random variable with 0 mean and variance sigma square, and this is statistically independent of f and the approximating function g of x which depends on the data set D. So, throughout I would put this subscript D indicating that this approximating function is a function of this data set, and if we average this, in some sense we get an average curve. Okay. Now, what are we interested in? We are interested in the expectation of this. So, I fit a curve g of x that is a function of this data set D, and then I look at the deviation of this function g suffix d of x minus y. I look at this quantity, I square this quantity and I want to average this error over all data sets and the points x that I have. This is an important detail because I can have a distribution over the data sets and the points x can have a distribution. So, therefore, I am looking at this joint distribution between x and D. Now, our y equals f of x plus epsilon. So, therefore, I plug that in and I do the averaging over data sets and the points. Now, you can split this, for example, the way you know if the data sets and x are sort of independent, you can take D and x to be statistically independent and it basically factors with respect to the marginals of D and x, but in general it may not be the case, right. So, you can split this quantity dx as the distribution over D and x to be p of x times p D given x, that is the probability density on x times the probability density on the data set given x, and this is, you can exchange them, you can take D and x given D and you can exchange these expectations in some way, assuming that you can do so. Since we deal with finite data sets, you can do this exchange carefully without pathological cases. Okay. So, what we do is the following. So, we first fix an x, some data points, right, and now we look at all those data sets conditioned to the set of points and we average this over the squared quantity here, which is gd of x minus f of x minus epsilon. Now, once we set this up, it is sort of straightforward. We have to expand the terms inside this braces. So these terms we have to expand. So I have a plus b plus c form, a whole square, a square plus b square plus c square plus 2ab plus 2bc plus 2ca, right. We just invoke that identity that we learned from high school. So what we have is gd square x plus f square x plus epsilon square minus 2 times gd of x times f of x minus 2 times gd of x times epsilon plus 2 times f of x times epsilon, and this averaging is over x and d, which I split it conveniently in the form that I want, x and d given x, or I can do d and x given d. So whichever is convenient, and I can exchange these expectations to the level that is convenient to me. So I will go with this kind of splitting x and d given x. It makes more intuitive sense because I choose some set of points and then I look at those data sets containing these points and then average over the data sets and then average it over x. Now expectation is linear, so we will evaluate some of these terms towards simplification. So when you take the expectation over d given x of f square x, that gives me f square x because it depends on x, and the expectation over d given x of epsilon square is epsilon square because it is the same across all the data sets, the noise is the same. Now expectation of d given x times gd of x times epsilon is 0 because noise is statistically independent of this function gd, and it is 0 mean. So therefore you take the product of these two expectations, it is 0. Then similarly expectation of this quantity f of x times f epsilon over d given x is 0, the same reasoning as we did earlier. Now what we do is we define this average of this gd of x, that means I am doing a curve fit for this data set d, and I take this average curve averaged over all the data sets conditioned to this x, and that gives me this g bar as a function of x. So let us simplify this slightly. So now I have all these terms. So what I do is I have expectation of d given x g d square x, I add and subtract this quantity which is g bar of x, right. This is basically averaged over the data points given x. Now I simplify from my quantities that I computed earlier, those terms that were 0 I just ignore them, and I am left with these terms, which is f square x 2 times g bar x f x with a negative sign and then epsilon square with a positive sign here. Now what I do is I look at this quantity, the expectation over d given x of this quantity g d square of x minus g bar of x square, and I call this variance of x. Similarly I expand this out, which is g square plus f square minus 2 g bar x f x. I try to take this quantity and then I will simplify. Let me call this term 1, term 2, and this quantity is term 1. So I simplify term 1 to be variance of x, and I take this quantity term 2, which is g square x minus g bar square x minus 2 times g bar x f x plus f square x, and this is in the form of a square minus 2ab plus b square form, and I can write it as a minus b square. So I have this quantity inside the expectation over x simplified as g bar of x minus f of x, and this square would be essentially the so this is the bias and this expectation is what I am computing over x. So this is a bias as a function of x, and when I do this expectation I get this this bias which is averaged over all x. So what I land up finally is I have a variance term. So this was depending on x because I was looking at the conditional d give on x. So therefore it was a function of x, but when I average it over all x I get variance which is some quantity depending upon the distribution of x. Then I get this bias when I average it over all x, and I am left with sigma square, which is basically expectation over x and d, this noise statistic. So what it means is this error that I compute, which is averaged over the data points x and the data sets d, is having 3 terms. One is the bias, the other is the variance, and then sigma square which I have to live with. Now if that error is fixed, right, then if I increase the bias the variance is reduced, or vice versa depending upon how I fit my curve and how I choose my my sample of functions. If I have just one function versus have hypothesis with various functions that are defined over different sets, right. So now there is a trade off here between bias and variance, and often we live with this dilemma how to choose a function which is striking a good trade off. We may have some requirement in terms of our bias, some requirement in terms of the variance, and we can kind of optimize our regression problem given these quantities. So this is a very important detail, and I hope you like the analysis. So when you do regression problems particularly, so here we considered the analysis for a square error, but you can do other performance functions and derive similar analysis over different performance criterion that you may think about, for which you may have to do these analysis in a rigorous way and then see the trade offs associated.
In this case we consider epsilon square to be constant across all the data sets. Is that assumption necessary for this derivation?
That is a good question. Epsilon square does not have to be constant over all these data sets, and we are not limited by this assumption. So there is a small fix that we can do here. This is right, expectation over x and d of epsilon square is sigma square. So what I could do here is when you take the expectation over all the data sets conditioned to x, that can give me some sigma square that depends on x, and when I average it over all x that gives me sigma square consistent with what we have. So I think we can make a small fix here. So it does not have to be the same across the data sets, and this quantity is going to be sigma square underscore x, indicating that it is conditioned on x, that it depends on x, and when we average it over all x then we get sigma square. I hope this clarifies your question. So I think this fixes all the details here. So I think this sort of covers the bias variance dilemma. So hopefully when you do regression problems you will be careful about what you really want and how you can strike a balance between these two quantities. So we will end this lecture here.